Black holes. I mean, if you ask pretty much anyone what they know about them, you're going to get one answer.
Oh, yeah, it's unanimous.
They're the ultimate cosmic drain.
Right.
Right. Nothing gets out.
Absolutely. Light goes in, time does weird things, and gravity always wins. End of story.
Exactly. It's like the one piece of pop science everyone just knows. A black hole sucks everything in, period.
It's the point of no return. That's what the event horizon, the Schwarzschild radius, or ARCS, is all about. Causally, if you cross that line, you're not coming back.
Right. But if you're here for this deep dive, you're not here for the basics. You want to know what happens when general relativity gets weird.
Uh-huh.
And today, we are diving into source material that shows that this common belief, this idea that everything falls in, it's actually violated, specifically for light that starts really close to that boundary.
And that's our mission today. We're going to unpack a paradox that, from a normal Newtonian point of view, just sounds completely absurd. We're going to show how light, a massless particle, can actually defy a black hole's gravity.
Okay, let's just put the main claim right out there because it's a big one. The source material is very specific. It says, if a beam of light starts out close enough, and that distance is less than 3/2 times the Schwarzschild radius.
So 1.5 times that radius.
Exactly. If it starts there, even if it's aimed towards the black hole, the curvature of space-time can actually bend it around and it escapes. It gets out.
It's an incredible claim. And the flip side is just as strange. In that exact same region, if you aim light away from the black hole, but it has enough sort of sideways motion, enough angular momentum,
It falls in.
it turns back around and falls in. It just shows you how completely twisted the geometry is right at the edge. The rules just, they reverse.
So to ground this whole conversation, the sources give us a couple of key ideas we need to keep in mind. First is this concept of the innermost stable circular orbit, the ISQ.
Right. The ISQ is critical. It's the closest you can get in a stable orbit. Any closer, and you just spiral in no matter what.
But the sources point out something really interesting about a specific type of black hole, the Reisner-Nordstrom one, the charged one.
Yeah, for an RN black hole, the math shows its ice-Canera can be exactly at the event horizon, which tells you that even the idea of an immediate plunge isn't universal. The area just outside Ascara is, well, it's a territory of really complex physics.
And that brings us to the second anchor point, the number we have to burn into our brains for this deep dive.
3/2.
1.5 times the Schwarzschild radius.
This is not some random number. It is the precise, mathematically derived boundary that dictates everything for a photon. It's where the normal rules of gravity stop and this new paradoxical behavior begins. And we're going to spend a lot of time today explaining exactly why that factor of 3/2 is so important.
Okay, so let's set the stage. To even begin to understand this, you have to understand the map, the mathematical landscape around a black hole. And for the simplest kind of black hole, non-rotating, no charge, which is what the sources focus on, physicists use a tool called the Schwarzschild metric.
The metric is basically the geometric rulebook for that bit of space-time. It tells you how to measure distances, how to measure time in this, extremely curved place. It's the solution to Einstein's equations for a simple spherical mass. It's our map.
And what's so crucial about this map is that it's actually simple in a way. If you look at the equation, the DS2, you see that it doesn't depend on two things: time, t, and one of the angles, phi.
And those two facts are the keys to everything that follows. The fact that it's independent of time means the space-time is stationary. It's not changing.
It's stable.
Exactly. And its independence from the angle phi just means it's spherically symmetric. It looks the same no matter how you turn it.
And that symmetry, that consistency, is where the physics of conservation laws comes from. It's how we can calculate the path of anything, especially light, a path we call a geodesic.
Precisely. In general relativity, a symmetry like that gives you something called a killing vector.
Okay, hold on. A killing vector, that sounds...
Yeah, it does, but it's really just a mathematical tool that confirms a symmetry. The formal definition is that if you sort of drag the metric along this vector field, the metric doesn't change. It's a formal way of saying this direction is symmetric.
So it's like, if you're on a perfect merry-go-round, spinning it doesn't change the physics.
Yeah.
So there's a killing vector for that rotation.
That's a perfect analogy. And that symmetry, that killing vector, corresponds directly to a conserved quantity.
Which is angular momentum.
Exactly. And because the Schwarzschild metric doesn't change with time, there's another killing vector, kT, that corresponds to the conservation of Energy. Energy. So we have these two fundamental quantities, energy and angular momentum, E and L, that are constant for any particle moving freely through this spacetime. They are the keys to its entire trajectory.
And for light, we're talking about a very specific kind of path, a null geodesic.
Right. Null just means that the spacetime interval, ds2, is zero. It's the relativistic way of saying it moves at the speed of light.
So the power here is that we can take this really complex four-dimensional problem and by using the conserved E and L, we can boil it down to a much simpler one-dimensional problem.
We can, yeah. We basically turn it into a problem of a particle moving in a one-dimensional potential field. And that potential field is what's going to reveal this bizarre, non-intuitive boundary we've been talking about.
The potential field, which physicists call the effective potential, VEF.
So this is how we start to see where light goes. The source material uses this idea of an effective potential to simplify everything.
It's a really common and powerful technique. This VEF basically acts like an energy landscape. Imagine a hill. If a particle has enough energy, it can get over the hill. If it doesn't, it rolls back.
And this landscape, for light near a black hole, determines whether it escapes or falls in.
The source gives us the equation for it, and it's so elegant. VEF is equal to L2 over R2 times the quantity, 1 R.
Okay, let's break that down. The first part, L2 over R2. That seems familiar. It should. That's just the classical centrifugal barrier. It's from the light's angular momentum, L. It's a repulsive term. It tries to fling the light outward.
So that's the part that's trying to save the light, basically.
You could say that, yeah. And the second part, the 1 RS, that's the general relativity part, that comes directly from the Schwarzschild metric, and it represents the gravitational pull.
And that term is crucial because as your position, R, gets closer and closer to the Schwarzschild radius, HAS.
That whole factor goes to zero,
Right.
which means the effective potential, the entire barrier, collapses to zero right at the event horizon. Gravity becomes so overwhelming that the centrifugal force just can't compete anymore.
So we can set up an equation that's basically just conservation of energy.
Right.
The total energy squared, E2, equals the radial motion squared plus this effective potential.
Exactly. And a turning point where light stops moving radially and either falls back or escapes happens when that radial motion is zero. In other words, when E2 equals VEF.
So to find the most interesting point, this boundary of stability, we need to find the peak of that potential hill.
We do. And how do you find the maximum of any curve?
You take the derivative and set it to zero.
You take the derivative of VEF with respect to R and solve for R. And when you do the math, when you work through the calculus, you get a beautifully simple, profound result.
The peak of the potential, Rmax, occurs exactly at...
R equals 3 over 2 Rs.
There it is, 1.5 times the Schwarzschild radius.
That is the photon sphere. It's the one and only radius where light can have an unstable circular orbit, where the outward push of the centrifugal force and the inward pull of gravity are perfectly balanced.
So that's the aha moment. The real boundary that governs what light does isn't the event horizon. It's the photon sphere.
The event horizon is the causal boundary. The photon sphere is the dynamical boundary. And the value of the potential at that peak gives us the energy threshold we need. We can compare a light ray's properties to that threshold and know its fate.
Which is exactly what we're going to do next. Let's compare the trajectories. This is where moving just a tiny bit inside that 32ers boundary changes absolutely everything. Okay, so to make this comparison, the sources use a concept called the impact parameter, B. And specifically, the ratio 1b2, which is equal to E2 L2.
And that ratio is it's a great physical shorthand. It tells you everything about the light ray's initial aim.
How so?
Well, a high value of 1b2 means you have a lot of energy E compared to your angular momentum L. Physically, that means you're aiming almost straight at the black hole. Very little sideways motion.
A radial shot.
A very radial shot, yeah. And a low 1b2 means you have tons of angular momentum. You're skimming past it, more of a glancing blow.
Got it. Okay, so let's start with case 1, far from the black hole.
Yeah.
We're outside the photon sphere, so R is greater than 32.
This is the region where things make intuitive sense. The potential acts like a normal hill, gravity pulls, and you need to have enough sideways motion to not fall in.
So first outcome, the plunge. This happens if you're aimed pretty much right at it, right? High 1b2.
Exactly. If your 1b2 is greater than the peak of the effective potential, you have more than enough energy to clear the barrier. The light just spirals in and crosses the event horizon. Gone forever. That's what we expect.
Okay. What if you have the exact right amount of energy? Your 1b2 is equal to the peak of the potential.
Then you get trapped right at the top of that hill. You enter that unstable circular orbit precisely at r equals 32.
A photon sphere.
You're perpetually falling, but the centrifugal force is holding you up. It's a perfect balance, but it's unstable. The tiniest nudge sends you either spiraling in or flying away.
And the third option, scattering. This is for a light ray that's aimed far away with low 1B2.
Right. Not enough energy to get over the potential hill. The light comes in, it slows down as it climbs the potential, reaches a closest point, a turning point, and then it just rolls back down and gets flung away. It's deflected.
That's gravitational lensing.
That is the essence of gravitational lensing, yeah.
Mm.
So outside 32s, everything works as you'd think. Aim close, fall in, aim far, get bent away. But now we move inside.
Now we cross that line into the region between the event horizon and the photon sphere. And this is where it gets really interesting.
The whole energy landscape flips on its head. The geometry is so warped here that the roles of the forces, they effectively reverse.
Okay, let's start with the big one, the paradox. A light ray aimed towards the black hole. High radial momentum, so 1B2 is greater than the potential.
In the far region, that meant a guaranteed plunge. Here, in this inner region, it means escape.
It gets out. Light aimed at the singularity gets out. How? Why?
Because the geometry inside 32s is just, it's bizarre. The curvature is so extreme that for a nearly radial light ray, it actually bends the inward path so sharply that it turns it outward. It lets it climb out of the potential well on the other side.
So it's like the black hole is trying to pull it in,
Yeah.
but the road itself curves so sharply it forces the car to turn and drive
So
away.
that's a fantastic analogy. The road is space-time, and it bends you to freedom. The energy barrier to escape from inside the potential maximum is actually lower.
So what about the inverse? Light aimed away from the black hole with a lot of angular momentum. Low 1B2.
That's the light that gets captured. It starts moving away, but it hits a turning point in the potential and gets pulled back in.
So the very thing that saves you far away angular momentum dooms you when you're close.
It becomes your fatal flaw. It pushes you just far enough for the insane gravity in this region to grab hold and pull you back. It's like a gravitational mirror world. What helps you out there hurts you in here.
Which brings us to the most extreme case, the exception, the purely radial ray,
Right. For a purely radial ray, the angular momentum L is 0.
which means 1B2, E2 divided by 0. It's infinite.
And infinity is always, always greater than the finite potential barrier, so the escape condition is always met.
Meaning any light ray that is aimed perfectly radially or even close enough to perfectly radial.
It will escape from this near horizon region. It only gets captured if it has enough of a sideways component, enough angular momentum to hit that turning point and fall back.
It's an incredible dependence on the initial angle.
It really is.
Yeah.
Which leads to the next logical question. What is that angle? How much can you be off by before you're doomed?
Right. We need to calculate the critical angle. Psi-critical. This is the threshold, the edge of the escape cone.
Exactly. If you launch your light at an angle less than this critical angle relative to the radial direction, you get out. Any angle larger than that, and you're providing too much angular momentum and you fall in.
And the sources show how to calculate this using the components of the light's velocity. It all boils down to an equation for the tangent of that angle, tan PS.
Yep. And the final expression for that critical angle only depends on where you are, your radius r and the size of the black hole, IRs. It's a purely geometric result.
So let's test the boundaries of this weird zone. First, let's start right at the photon sphere, r equals 2 ors.
If you plug that radius into the critical angle equation, the result you get is that tan psi critical goes to infinity.
Which means the angle is 90 degrees, pi over 2 radians.
Exactly, and that makes perfect sense. It confirms what we already know. To stay in an orbit at the photon sphere, your motion has to be purely tangential, exactly 90 degrees to the radial direction.
So right at the edge of this zone, you have a huge window to escape. You can basically shine your flashlight sideways, and the light still has a chance.
But now, let's go to the other boundary. Let's go right to the event horizon itself. R equals R?
What happens when you plug that into the equation?
The result is tan psi critical equals 0.
0.
Which means the critical angle itself is 0.
So the only way out is a perfectly straight radial line.
That's the stark reality of it. At the event horizon, the only light that can even theoretically move outward is light that is aimed perfectly radially. Any deviation at all, no matter how tiny, and the trajectory is doomed to fall towards the singularity. The escape cone has pinched shut to a single line.
Wow. And that mathematical result leads to this. this really powerful analogy the source uses, the dimming flashlight.
It's a great way to visualize it. Imagine you're holding a flashlight and you're moving from the photon sphere inward toward the event horizon. And a friend is watching you from very, very far away.
Okay, so at our illy kick, overly 30 U2 airs. That escape cone is wide open, 90 degrees. A huge fraction of the light from your flashlight can get out and reach your friend. They see a bright light.
A very bright light. But as you move closer to tours, that critical angle shrinks towards zero. The cone of light that can escape gets squeezed into this impossibly narrow beam aimed straight out.
So to your friend far away, the flashlight just seems to get dimmer and dimmer.
Exactly. Not because the bulb is failing, but because the geometry of spacetime is closing a shutter, blocking almost all the light from getting out. The solid angle for escape is shrinking to nothing.
And at the horizon, it's completely dark.
The fraction of light that escapes goes to zero. It's a beautiful, tangible way to see how 32 Tours is the real place where the optical action is happening.
It's all just geometry. It's incredible. But these results are so strange that I think we need to just take a second to talk about the rigor here. This isn't just a fun thought experiment. This is baked into the math of general relativity.
Oh, absolutely. The sources are very clear on this. These are direct, logical consequences derived from the formal mathematics of differential geometry. This isn't an approximation.
We're not in flat Euclidean space anymore.
Not at all. And the source material validates every step. They use the Lie derivative to formally prove the symmetries we talked about.
Right, the LK gab equals 0. You can't just use a normal derivative because space itself is curved. You need a tool that accounts for that curvature when you're checking for symmetry.
It's how you prove rigorously that you have a true isometry, which in turn guarantees your conservation laws for energy and angular momentum.
And those laws are built on the geodesic equation, nabla u il 0, 0, which just says the light is following the straightest possible path through that curved spacetime.
Correct. And the math shows that as the light follows that path, the quantities E and L remain absolutely constant.
So there's a clear logical chain. The metric's geometry dictates the symmetries give us conserved quantities, and those conserved quantities let us build the effective potential.
Which reveals the counterintuitive boundary at 32. It all connects. It's a robust and, frankly, beautiful result of Einstein's equations.
It's just a powerful reminder that our flat space intuition just fails completely in these extreme environments. So, after all that, what does this all mean for you? We started with this simple picture of a black hole and, well, we've made it a lot more complicated.
And a lot more interesting.
Definitely. There are really two big aha moments to take away from this deep dive.
The first is that the true dynamical boundary for light around a Schwarzschild black hole isn't the event horizon, it's the photon sphere, at 1.5 times the Schwarzschild radius. That's the line that separates expected behavior from, well, from paradox.
And the second takeaway is just how weird that paradoxical region is. The near horizon zone where the rules flip. It's this gravitational mirror world where aiming gets you out and aiming out can get you trapped.
It really shows that gravity isn't just about pulling. It's about bending and distorting and reshaping the very fabric of space-time, especially right near the edge.
And for an astrophysicist who's actually trying to observe a black hole, 30 Tours is the number that matters. The shadow of the black hole we see in images. That's directly related to the size of the photon sphere, not the event horizon.
Which brings us to a final provocative thought.
Let's hear it.
So, we established that a purely radial light ray, with L00, always has the condition to escape from inside the photon sphere.
Right.
And we also established that right at the event horizon, the critical angle for escape shrinks to 0, meaning only a perfectly radial ray could even theoretically get out.
So, what if you could launch a perfectly radial light ray with L being exactly 0 precisely at the event horizon?
The geometry says it's aimed along the only possible escape path. But we also know that at the event horizon, there's infinite gravitational time dilation. An observer far away would see that photon take an infinite amount of time just to leave the horizon.
Does it escape?
Does the concept of escape even have meaning at that infinitesimal boundary? Is the photon following the outward path, but just frozen in time forever from our perspective? Or is it something else entirely? The math gives us a limit, but the physical reality at that limit is, well, something to think about.